Hello, hi. Uh, Welcome to the third part of the topic of our topic integration. So last video or last lesson we mentioned the definite integration. So in this video or in this lesson I will go through the definite integration and areas under the curves. Integration and area. An important application of integration is to find areas and volumes, and in fact, many of the formulas we already know for calculating areas and volume being found using the integration. So consider the graph of a function like the graph here. So we can see like that the shaded area is called the area under the function or the area under the curve, and as you can see it's bounded by the x-axis here, and so this is the x-axis and the two vertical lines where x equals a and x equals b, and on this example x equals 0 and x equals 1, and also bounded by the curve itself, the red curve here, the red function. So the area, the shaded area here, it's bounded by the curve, the x-axis, and these two vertical lines which represents the values of x, a, and xb as the limits for the integration basically. Also, this is from the previous slide lesson, just to remind you, and that's just repeating of what I just said on the previous slide. So the definite integral, where we have integration or integral sign, and it has upper limit which is b and lower limit which is a, f of x dx or y dx. So the integration of a function will give us the area, between the curve itself and the x-axis and the two lines where x equals a and x equals b, provided that the curve lies on or above the x-axis. So when the curve is on or above the x-axis, the area in that case will be positive. If the curve crosses the x-axis and becomes under the x-axis, in that case that means the area will be negative, so we need to deal with it because we can't have area as negative, so we need to put a minus sign in the front of the integration, and you will see that in the example. Okay, so in this example here, finding an area, find the area for the integral of 3x squared plus 2 dx. Okay, and the limits from 0 to 1. So these are the limits, so that's x, xa and xb. Okay, and this is the curve, and this is the area under the curve here. Okay, so basically to find this we need to find the integration of this function and the limit from 0 to 1. Okay, all of this area here. Right, so to integrate this, basically just a basic one, 3x squared is going to be like 3x cubed divided by 3. Yeah, so this is the first step. It's going to be 3x cubed divided by 3 plus 2x. And shall we put plus c? No, because we can't put c when we have limits. It's wrong. Yeah, so now we will have the limits from 0 to 1. Okay, now if I'll just want, right? So Now 3x cubed, so we cancel these 3's together, then we end up with x cubed plus 2x from 0 to 1. Okay, and now what we need to do, to apply the limits to the function, we need to replace or substitute the values of the upper limit here, which is 1, for x. I'll just take this off. Okay, so what we will do here, we will substitute the upper limit, which is 1. We'll substitute the upper limit 1 for x, and after we finish from substituting the value of 1 here first time, we substitute the value of lower limit for x, yeah, and we subtract them together. So what we will do, we will substitute each x here by 1 first. So this is going to be 1 cubed plus 2 times 1. Each x, I will replace it by 1. I finish the function, I close the bracket, then we do minus, we subtract, then start another bracket, and now I will substitute each x by 0. So this is going to be 0 cubed plus 2 times 0, yeah, which is 0 basically. I just wanted to show you the steps basically. So that was when it is 1 plus 2 times 1. Right, so this is going to be 1 cubed, which means 1 plus 2 is a 3. So this is a 3 minus, and 0 to the power 3 plus 2 times 0, it's all 0 here. So the answer is 3. Okay, so now I will rub this out and go through the slide to show you the work. Okay, so the shaded area equals a 3. Oh, no, I didn't work it out. Okay, it's good that I work it out. So I'll just write it down again then for you here. It's going to be like, as we said, 1 cubed plus 2 times 1 minus 0 cubed plus 2 times 0. And that is 3 minus 0, which is a 3. Okay, so the shaded area equals a 3, and we don't need to put units in this kind of areas when we find it from the integration. You don't need to worry about it. Okay, in this example here, or in this graph here, it's showing us there is a curve, the red curve here, and the area, the shaded area here between the x-axis and the curve. So this is the x-axis basically. Yeah, and the curve is the red line, as you can see. So we are like in this example showing to find like this area here. And because this area is above the x-axis, therefore it's going to be positive, so we have no problem with it. So to find the area of this part, we will just say the integration of x squared minus 2x dx, okay? And this will be x cubed over 3 minus 2x squared over 2. And the limits, it depends on, like, they didn't put the limits here. Maybe it's minus 1 and 0. So minus 1 to 0. Okay. Right, yeah. Minus 1 to 0. I'll just take this off. So, right, so the area is the integration from minus 1 to 0. On this graph here, we can see the shaded area here, it's under the x-axis. So So this is the x-axis, as you can see, and the area here is under the x-axis, and the limits are from 0 to 1. The limits are from 0 to 1. This is 0 basically, and this is 1 here, right? And as you can see, this green shaded area is under the x-axis. So when we will do the integration for this area, because it's under the x-axis, it's going to be negative. And in fact, yeah, we can't have a negative area. So we need to, what we need to do is put a minus sign before the integration. Yeah, we need to put a minus sign before the integration to get rid of the minus. Okay, so for part of the curve which is below the x-axis, the definite integral is negative. Therefore, we do the area of B, which is this one here, is equals minus the integral from 0 to 1 x squared minus 2x dx. So if you have the part of the curve you're integrating is under the x-axis, then you just put minus in the front of the integral to make it positive, because we can't have an area as a negative area. Have you heard one day about the area of a square, or the area of the house or a land is minus 12 meters squared? It has to be positive, or any number, right? This is this is like same example. That's the graph, finding this area here, and the limits is from minus 1 to 0. So this is the upper limit, the 0 is the upper limit here, and the minus 1 is the lower limit. So this is upper limit or boundaries, and this is lower limits. Okay. Right, so now after we do this, we need to integrate. So x squared is going to be x cubed divided by 3 minus 2x squared divided by 2. We'll cancel these 2's, and then after that we substitute the upper limit for x, and then minus substituting the lower limit for x. So this, when you substitute the upper limit, which is 0, that means 0 over 3, which is 0, minus x squared, which is 0 squared. So it's basically all 0 minus, and then we substitute minus 1 for all the values of x, and minus 1 over 3 minus 1. Well, minus 1 squared is plus 1 here. So that minus times plus is minus, and then there's minus outside. It's going to be plus. So the area here is 4 over 3, because the area here is 4 over 3. So you can just work it out and check the answer. Right? Because there is minus here outside. Okay, for the second part here, where we said the curve is crossing the x-axis, that means the area is going to be negative. So we need to put the minus in the front of the integral, or what they did here, they put it in the front of b. I think it's better if you just put it in the front of the integral so you don't forget about it. Okay, so that means you just integrate this, so that's x squared. It will become x cubed divided by 3 minus x 2x squared divided by 2, which is x squared, and the limit from 0 to 1. And then you substitute the values, and the answer is minus 2 over 3. And then because you multiply this by minus 1, yeah, if you put the minus here at the front, then there's going to be minus 2 over 3 times minus, and the answer is going to be 2 over 3. Okay, so that's the area of the negative part. Or if you want to keep it like this example, they put it in the front of the b, and so it's like, this is like minus b equals minus 2 over 3. Then multiply by minus 1 or divide by minus 1, you will get 2 over 3. Okay? So it's up to you. I'll just leave it as the example now, so I don't want you to confuse which one is which. This is how they wrote it in the example, but also you can just put it in the front of the integral and carry on. You don't need to put it in front of b. Okay. This kind here is different kind of questions where you have a curve and a line, and they intersect together, and you need to find the area like between them here. So this question, find the coordinates of the points of intersection of the curve and line shown, and find the area enclosed by the curve and line. So basically they just want you to find this area here, which is enclosed by the line and the curve. Okay. And also you need to find the coordinates of the points of intersection. So to find the points of intersection, basically because the curve and the line, they intersect, that means they meet at one point, yeah? So this means like this point here and this point here. So that means the x and y values are the same. So both of them have the same value of y in this case and x. So because of that, we can say, to find the points of intersection, the equations for the line, the equation for the line was y equals x, and the equation of the curve was 2x minus x squared. Okay, so because both of them they intersect, that means they have the same value of y, so we can make them both equals. So we can say y, which is equals x, and sorry, I'll just take this away. Okay, so this we can say x equals 2x minus x squared. Yeah, so I took this and this and make them equal to each other because both of them equals y. All right, and that's what we get here, and then rearrange, so it's x squared minus x equals 0, then x equals either 0 or 1. So basically these two values, it represents the boundaries or the limits of our integration. So these points of intersection are critical in finding the bounded area. So our area here, it's bounded between x equals 0 and x equals 1. Right. So the area required is the area under the curve between 0 and 1. Okay, so this is the curve, this is 0 here, and that's 1. So it's the area required is the area under the curve minus, take away, the area under the blue line here, okay, which is the triangle basically. So as I showed you in the previous graph, that's basically they want this area here. which is bounded between the curve and the line. Right. So to find this, we find area under the curve. So the curve was 2x minus x squared. So we find the integration for 2x minus x squared and the limits from 0 to 1. So this is going to be 2x minus x squared from 0 to 1. We integrate this and this is going to be 2 over 3. And then area of the triangle is half times 1, which is 1/2. Okay, because it's the area of the triangle. Because right, the area of the triangle is half times base times height. Yeah, the area of the triangle equals half times the base times the height. So in this example, if you look at it, the base is from 0 to 1, so that means it's 1. So the area of the triangle is half times 1 times the height is 1 as well, because we have y equals x. So therefore, if x equals 1, therefore y equals 1 as well. Yeah? So if x equals 1, therefore y equals 1. So it's half times 1, which is 1/2. That's the area of the triangle. So that's why it's half times 1, which is 1/2. So that's the area of the triangle, and we found the area of the curve. Therefore, we will subtract the area of the triangle from the area of the curve. So that's why we have 2 over 3 minus 1/2, which is give us 1/6. That's the area, the required area on this example. So that's method 1. There is another method, which is instead of finding the two areas and then subtracting them. So instead of finding the area under the curve and the area under the straight line, or which is the triangle area, we can subtract them at the beginning and before do the integration, and then we integrate. Okay, so we get here like 2x minus x squared minus x, because the function for the curve was 2x minus x squared, and the function for the line is y equals x. So we subtract them together before we start the integration. So that's 2x minus x squared minus x, that's from the straight line. And then this equals x minus x squared. So we will integrate this x minus x squared and the limits from 0 to 1, and we apply the upper limits and the lower limits and we subtract them, and that will give us the same answer as 1 over 6. Okay, so any method is fine as long as you work it correct. Okay, another example here. Find the points of intersection of the following curves and lines. Show the graphs in a sketch, shade the region bounded by the graphs and find its area. So we have these two equations, y equals 6, so that's one of them, and the other one, y equals x squared plus 2. So basically we know y equals 6, and because it's a point of intersection, that means both y's are the same. So again, we can make x squared plus 2 equals 6, and then we solve it from that point. Rearrange, etc. We get x equals, because x squared equals 4, therefore x equals plus minus 2. And as I said earlier, this is very critical to decide our limitation or boundaries. So basically the values of x, it's the limits for the integration. So now we know that our limit is minus 2 as a lower limit and to 2 as an upper limit. and y equals 6 for both points. We know that. Yeah? So in this question, they want this area, which is between the line y equals 6 and the graph. So it's the area here they want, it's between these two. It's not under the curve. It's between the curve, and the line. So the shaded area here, it equals the area of the rectangle, which is the whole rectangle here. Yeah, all this as a rectangle, minus the area under the curve. So the area, the shaded area, it's like, I'll just use the highlighter to show you that. It's like the area of this whole rectangle. Yeah, minus this area which is under the curve. So the whole, that's whole including from here. It's like a rectangle. Minus the area under the curve, which is this. All this. So if we subtract them from each other, we can get the pink area, basically. Okay. And now, so area under the curve, finding the area under the curve, we use the equation or the function of the curve and the limits from -2 to 2. Okay. And we apply the limits and that will be like here it's like 2 to the power 3. Yeah, so this it's like 2 to the power 3 and plus 2. Well, just do it actually next to it. Don't worry. Yeah, so this is like 2 to the power 3. Oh, that's 2 to the power 3 over 3 plus 2 times plus 2 times 2. Okay, minus, and then you will substitute -2 here, -2 to the power 3 over 3 plus 2 times -2, which is -4, and this will give you 8 over 3 plus 4 minus -8 over 3 minus 4, and that's equals 16 over 3 plus 8, which is 40 over 3. This is the area under the curve, which represents the green area. And to find the pink area, which is between the curve and the line, which we call it the shaded area here. So the shaded area is area of a rectangle minus the area under the curve. So we already found the area under the curve, which is 40 over 3. Now we need to find the area of a rectangle, which is, this is 6, and the x-axis here is 4. So the area of the rectangle is 6 times 4, and that's 24. So area of the rectangle, yeah, equals 6 times 4, which is 24. So therefore we can say the shaded area equals area of a rectangle, that's 24, minus the area under the curve, which we found here as 40 over 3. And sorry, and that's, after you work it out, will give us 10 2/3. Okay, I hope that's clear now. Okay, if a curve crosses the x-axis between the limits of integration, So part of the area will be above the axis and part below. So for example, y equals x cubed between -1 and +1. So what they are saying here, if a curve across the x-axis, yeah, between the limits of the integration, so part of the area will be positive, which is above the x-axis, and part of the area will be under the x-axis. In that case here, it's going to be negative. Okay, so the symmetry of the curve, so this curve here, it has a symmetry, like both sides are the same. So the symmetry of the curve means that the integral from from -1 to 1 is 0, because because of the symmetry. Then the integral from -1 to 1 is 0. But to find the area for both of them, we could find the area or integrate from 0 to 1, which is this area, the positive one. So we could find this area here and times it by 2 because of the symmetry. Yeah? So we double the answer. But for a curve which wasn't symmetrical, we could find the two areas separately and then we add them together. So in this example, just because of the symmetry of the curve, so we can just find the area here on the positive side from 0 to 1 and then double it or multiply it by 2. But if the case is different, like we have a curve and it's not symmetric, then we could find the area, the two areas separately, and then we add them together. And that's it for this lesson. I hope it was easy to follow, and I would like you to do some questions from the book regarding this topic, and I think it's page 216, exercise 2.2. Okay, so have a nice day, and if you have any question, let me know. Thank you and take care. Bye.